In this video, I want to talk about test benches in System Verilog. So test benches are generally HDL code that are being used to test another module, and that module is usually referred to as the device under test or DUT. So test benches, they are not synthesizable. Their only purpose is to basically test whether a module is working properly or not. So there are three different types of test benches. We can have simple test benches, which only provide some value and record the outputs of the module. We have self-checking test benches, which provide the inputs, read the outputs, and check whether the outputs are correct. And then we can have more advanced test benches with self-checking with test vectors. So let's just go through one example from each. So let's just consider one very simple example. We want to write a module that implements this function. We call it the silly function. So y equals b bar c bar or a b bar. So the implementation of this function is very straightforward. Since it's only one statement, we can simply use the continuous assignment or the assign keyword to implement that. So we have module, end module, silly function. The inputs are logic values, each being 1 bit, A, B, and C, and the output is a logic value y, which also has 1 bit. As for the value for y, we have y to be equal tilde b and tilde c, or a and tilde b. So this is basically the implementation of the above statement that we have. For a simple test bench, as I said before, we only provide the combinations of input that we can have for the circuit, and we record the outputs. So a test bench module doesn't have any inputs. What it has some internal nodes. So for the test bench that we want to use for testing the silly function, we have 3 internal nodes or internal variables, A, B, C, and 1 output variable, Y. So what we do is that we create an instance of the silly function and we call it the device under test or DUT. So we have silly function space DUT A, B, C, and Y. So what this line does is that it creates one instance of the silly function and it assigns the inputs and outputs in this format. Then we have to go through all the individual possible combinations of the inputs. So what we basically do is that we use the initial keyword that basically initializes the process of checking, and then we begin. So any combination that we have falls between the begin and end. So as we can see, at the beginning we assign A to be 0, B to be 0, and C to be 0, and we have hashtag 10, which basically means that we stay in this state for 10 units of time. After that, we change the value for C from 0 to 1, and then we wait 10 units of time more. So we have 0, 0, 0, and then we go 0, 0, 1, and then we change B to 1 and C to 0, so 0, 1, 0, and then we change C to 1, so 0, 1, 1. So at any given time, what this function is actually doing is basically changes the inputs of A, B, and C and records the value for Y, or simply just shows the value of Y, right? So this is a very simple test bench. There is no check for whether the outputs are correct or not. So that brings us to the other type of test bench that we can have, which is a self-checking test bench. So for the self-checking test benches, we have some of the lines as before. So basically we have the internal variables a, b, c, the internal variable y, and also we have the instance of the silly function with inputs a, b, c and the output y. But now this time what we want to do is that we want to check whether the values are correct or not. So if you see from the function, y was b bar, c bar plus a b bar. So let me just double check. Yes. So what should be the value of function y when a, b, c are basically 0? A equals b equals c equals 0. So when a and b and c are 0, this part b bar c bar is 1, while this one is 0. So y is basically 1. So what it happens is that we check the value for y whenever a new value is being created. So we assign value of a to be 0, b to be 0, and c also to be 0, and then we wait for 10 units of time, and then we read the value for y. We check the value for y. If the value for y is not 1, we display that 0, 0, 0 has failed, so we display a message. Then we do the same for the next possible combination, and we check whether the output is correct or not. Remember, since we have the Boolean function, we can know what is the correct output. So that's why we can basically check whether the synthesized circuit is actually producing the correct outputs for us. So not necessarily the synthesized circuit, but the module that we have created. So if it is doing what it is supposed to do, then we can synthesize it. Otherwise, we need to basically troubleshoot and see what's wrong. And this process is being done for all the possible combinations. But you can see that when the number of possible combinations is a lot, it is not easy to list them out like this, put them in if else statements, right? So usually what we do is that we create test vectors for all the possible combinations of inputs and outputs, and then we load them into the test bench that we have. So that brings us to the third type of test bench that we can have. In this type, we have a test vector file which lists all the possible inputs and expected outputs. So for the test bench, we first create a clock for assigning the inputs and reading the outputs. Then we read the test vectors file into an array, and we assign the inputs and we record the expected outputs. And then we compare the actual output with the expected output and report the errors, right? So as you can see, what is different between this one and the previous case is that we record all of our possible combinations and outputs in a separate file, right? So this way we kind of eliminate the need for having many if-else statements, one line after another, right? So to create the clock, what we basically can do is that this clock signal can be used to provide timing for when we assign inputs and when we compare the outputs with the expected outputs. So we usually assign inputs on rising edges of the clock and we compare the outputs with the expected output on the falling edge of the clock. So this test bench clock can be used for testing synchronous sequential circuits as well. So we don't have to have, let's say, a separate clock that is coming from outside. We actually can create the clock inside the test bench. So here you can see a test vector file example for the silly function that we have. So it is called example.tv, TV short for test vector, and this contains these lines. in which the first three values are basically the input values. We have underscore, and then we have the expected y. So this is simply the truth table that we have that shows the relationship between any combination of the inputs and the output that we need to have. So now let's see what we need to do. The first thing was to generate a clock. So inside the module, first we define our internal variable. We have a clock, reset, A, B, C, and then the expected output, and then the actual output. We defined some additional variables for bookkeeping and also for reading the array of test vectors from the test vector file. And then we create an instance of the SILIP function that we want to test. So to generate the clock, we use always statement. So since there is no sensitivity list, this process executes always. So what it does is that it executes this statement, which says make the clock 1, wait for 5 units of time, and then make the clock 0, and then wait again for 5 units of time. So this process is going to be repeated indefinitely as long as you run the Testbench module. The next thing that we need to do is that we need to read the test vectors into an array. So the function that, the file that we have used for the test vectors is called example.tv, and we use an internal function of system Verilog to read that. So that function is $read member. So it reads the values of the test vector line by line, and it stores that into the test vector variable that we have. What else that we do is that we initialize the two bookkeeping variables that we have defined with 0. We make the reset 1, wait 27 units of time, and then we make the reset 0. And that is basically for the initial state of the system that we want to reset everything before we do the actual testing. What we said we do for the third step of the process is that we apply test vectors one by one on the rising edge of the clock. So to do that, we create an always statement. So this one, keep in mind, this is not always FF, right? It's always, and we have a sensitivity less, which is the positive edge of the clock. So we wait 1 unit of time, and then what we do is that we apply, we basically go through each one of the rows of the test vector one by one, and then we apply or assign the inputs and the expected outputs. And then for the on the falling edges of the clock, we check whether the output that is produced by the module is the same as the expected output. So this is done when the reset signal is 0. During the reset, we don't want to check anything. But if the reset signal is 0, we actually do the test. If the value for y is not equal to the expected y, we just display some error messages, and then we increment this bookkeeping variable errors that counts the number of errors that we have. You can imagine if you are working with functions that have more than 3 inputs, let's say several dozen inputs and many outputs, right? This is going to be very useful to not worry about how many inputs or how many combinations do we have, or how can we basically count the number of errors. One other important thing that you need to consider is that, generally speaking, glitches happen when we go from one set of combination to the other one, right? So using test vectors, it is possible to provide the inputs in different orders, so we make sure that we don't have glitches too. So, and then we repeat this for all of the rows in the test vector. So we increment the vector number, we go to the next one, and then we repeat the process until we get to the end of the test vector. So conceptually speaking, you should now have a good understanding of how test benches are being used. You should be able to distinguish between different types of test benches that we can have. And you should be able to explain what are the benefits and basically pros and cons of each one of those are. So for some cases, if the function is very simple, if the number of inputs is limited, you can use a self-checking test bench, and that should be enough. But for more and more complex modules, you definitely need to do self-checking with test vectors, so to avoid unnecessary lines of code that you may need in the process. Of course, a more advanced discussion of these things is out of the scope of this course, so you are referred to appropriate resources if you want to learn more.